We're now going to continue our look at some of these special discrete random variables with a pair of very important random variables called the negative binomial and the geometric random variables. Now, the reason why the word binomial is in this particular name is because in some sense there is a relationship between the binomial distribution that we've talked about and this new random variable that we're going to look at right now. So first up, what we're going to do is define what a negative binomial experiment is, and then maybe just do a quick compare and contrast between the binomial and the negative binomial, and then say how the geometric is related to this one. In fact, the geometric random variable is just a special case of the negative binomial. All right, so let's go ahead and define what we mean by a negative binomial experiment. Right, so a negative binomial experiment, right, or you could say process, but a negative binomial experiment has the following properties. All right, so the first thing that it has is it consists of X number of Bernoulli trials, right? So it consists of X number of Bernoulli trials. And if you remember the Bernoulli trials, those are trials where each trial may result in one of two outcomes, whatever we deem as success or failure, right? But now it consists of X number of those trials, right? Two. Right, so again, just so each trial, so this just kind of reiterates this point. So each trial results in either success or failure, right? And as usual, we denote the probability of success. So little p denotes the probability of success. Probability of success, and therefore 1 minus p is the probability of failure, which we can also call q, right? So is the probability of failure, right? And again, the trials are independent, right? So trials are all independent. Right? And what the thing that is really going to distinguish this type of experiment from our previous binomial experiment is that the trials continue so the trials continue until our successes are observed, right? So if you think about it, compared to the binomial experiment, let's see what the difference is. So in the binomial experiment, the number of trials were predetermined. So that was our n. So the n was fixed, and in those n independent Bernoulli trials, we were interested in the number of successes, right? Now we're saying that we don't know how many trials, which is why we're using our little x here, right? We don't know how many trials we'll have to perform. However, we're going to continue performing those trials until we observe a set number of successes. So you can definitely see the difference there. In the binomial experiment, the number of trials was fixed, and the number of successes, that was our random variable. Now, the number of successes will be fixed, and we're saying the number of trials is variable, right? And so the whole idea of like continue flipping a coin until you observe a head, right? Again, we don't really know how long it will take, right, before we see that success, right? So that is a negative binomial experiment. Let's see if based on this we can figure out, one, the sample space, and then two, the PDF, because if we can do that, then that gives us a good handle on this experiment, right? And once we have the PDF, then we know all those probabilities can be computed, all right? So this is saying we're going to continue our trials until our successes are observed. So at the very least, for instance, if we want to observe 10 successes, then the bare minimum of trials that we would have to perform would be those 10, right? Because we can't hope to observe 10 successes if we only perform the experiment 5 times, right? So let's write down what the sample space is. Right? So in other words, what are the possible values of x? Well, it can't be 0, because right, we can't, because remember, the number of successes is going to be predetermined, and it's going to be some positive integer, right? Because we're counting the number of successes. So at the very least, we're going to have to perform the experiment r times. That's what this says. The x represents the number of trials, and we want to see our successes, so we at the very least would have to perform it r times. If we are lucky, right, then we will observe those r successes in these r trials. So everything we observe would be a success, but that's not likely to happen, especially if our probability of success is low, right? But it might be that we might have to perform r plus 1 trials in order to see those r successes. Or maybe r plus 2, or r plus 3, or ... We don't know, right? And this is the sample space of a negative binomial random variable. It is now going to be countably infinite, which again is a contrast with the binomial experiment, where that sample space was fixed because we knew how many trials we were going to perform, and that put a limit on the number of successes we could have, right? So let's just note that this sample space is now countably infinite, right? Okay, so we know the possible values of x, right? So if we want to see 10 successes, then it's possible that the x will be 10, 11, 12, 13, and so on. And again, I don't know what that natural limit is, so I have to allow for maybe we just continue doing these trials and never getting that r success, right? But again, a lot of that has to do with the probability, which we're going to talk about now. So let's think of the ways that you could get those r successes, right? So so what I'm going to do here is say, on this trial here, this is where we will observe the rth success. And at that point, the experiment would end, right? Because that's what we're looking for. So for it to end right here, right, and we're saying that it's going to take this, so the rth success will be on this x trial. That's what we're saying. It's going to take x number of trials to see this rth success. Well, in order for this to happen, it means in the previous x minus 1 trials, I would have to have observed r minus 1 successes. So in all the other ones leading up to this, right, here I would have to have x minus 1 trials, and in those I would have had to observe r minus 1 successes. That's the only way I could then have the rth success on the xth trial. I would have to have just, I would have to have seen all but one of the successes on the previous trials that I would have performed, which would be just one less than this, right? But but now this sounds like kind of a binomial thing, where you want to have this many successes out of this many trials. So let's write that down. So based on the binomial experiment, then this would have to be our x minus 1 choose r minus 1, and then we would have to have p to the r minus 1, right? That would give us the r minus 1 successes. And then we would have to have the 1 minus p. And then what would I have to have? It would be the difference between this and this, right? In order to have the number of failures. Because I'm saying we're going to perform this many trials, and we're going to observe r minus 1 successes. That means, right? So let me say it this way. So we have x minus 1 trials. We would need to observe r minus 1 successes, which means I would have, the difference here would be the failures. So if I subtracted these, then I would have x minus r and then negative 1 minus negative 1. So the 1's would go away, and then I'm left with x minus r failures, right? So that would have to be the exponent of my probability of failure. So again, this many failures. And because of independence, these things get multiplied. So that's what would have to happen in the blue. And then I would have to have a success on the next trial. Well, the probability of getting a success on the next trial is again p, because it's a constant. It's one of our Bernoulli things where that probability of success doesn't change. And by independence, I would take this probability and multiply this probability, and then here is, so let me write it below. So here now, we'll put everything together along with the sample space and state the PDF of a negative binomial random variable. This will be it. So we'll have the x minus 1 choose r minus 1 times. Now when I multiply these, I have p to the r minus 1 times another p to the first power. Adding those exponents gives me p to the r, and then I have 1 minus p to the x minus r, right? So that's the PDF of my negative binomial random variable, and here's the sample space. So x could go from r, or it can be any value from r, r plus 1, r plus 2, and so on. All right? Now, we have a nice notation, just like how we use the b for binomial. We're going to use nb for negative binomial, right? So here is the notation. So we're going to say a random variable follows the negative binomial distribution, and the parameters here will be the your R and your P. It's your R that's fixed because that's the number of trials or successes you want to observe, and then your P is the probability of success on any given trial, right? So the parameters now are R and P, right? In the negative binomial, in the binomial case, the parameters were N and P because your N was fixed and you were counting the number of successes. Now your number of successes is fixed, that's your R, and we're counting the number of trials it takes to observe those successes, right? Now, with the negative binomial, we also have two very simple formulas for the mean and the variance. And I'll go ahead and write these down. And the mean for your negative binomial random variable, it's simply your R divided by P, right? So it's your number of successes that you want to observe divided by the probability of success on any given trial, right? So that's pretty straightforward. And then your variance is your R times 1 minus P over P squared, right? And these are pretty much all the equations that you need for the negative binomial. The one thing that's missing, and that's because of your countably infinite sample space plus the idea of all these, the different values for that R and P can take on, we don't have nice tables for the CDF of a negative binomial random variable. So what that means is any cumulative probability that we have to compute will have to be done via summation, right? And of course, that's taken into consideration when questions are being asked. It's like, okay, if we don't have nice, easy tables to access and there isn't a nice formula, then we have to make sure that you're not adding up, 20 of these to accumulate the probability. So all those things are taken into consideration, all right? So that's the negative binomial. Now, what is this whole geometric thing, right? Well, the geometric is just a special case where our R is equal to 1. That means we're counting the number of trials until the first success, right? So when R is equal to 1, all right, again, let me kind of explain what that means. When R is equal to 1, we are counting the number of, again, these Bernoulli trials up to and including the first success, right? So how many trials before I see the first success? So counting the number of trials up to and including the first success, right? And so this is called a geometric random variable. So this is called a geometric random variable. And basically, if we just go through and wherever there's an R here, just go ahead and put 1 in, then we have the CDF, we have the sample space, we have the mean and variance. And the notation there is we use G for geometric, and then since the R is a fixed number, it doesn't change anymore. We just put the probability of success in parentheses. So I'll state it so we can see what it looks like, right? So this is called a geometric random variable. Here is how it's denoted. G, and then you put your P there. And the CDF, or the PDF, right? Now, if R is equal to 1, then it means you're choosing, out of x minus 1 things, you're choosing 0 things. And if you express that in terms of factorials, you'll see that that will always be 1. So this whole thing goes away, which is great, right? Much easier to compute the geometric probabilities. And then you're just going to have p to the first power, so you'll have your p there. And then you're going to have 1 minus p to the x minus 1 power. So 1 minus p to the x minus 1. And then the sample space, now think of it, if you're looking for that first success, then you have to do the experiment at least once, or you might have to do it twice, or thrice, and so on, right? So again, it really does simplify when you look at the geometric situation where you're looking for that first success, and then your mean ends up being 1 over p, and then your variance ends up being 1 minus p. I guess I don't have to put that in parentheses now since it's just being multiplied by 1, so I can have 1 minus p over p squared, right? And just, kind of thinking about this, the mean for a geometric random variable is just the reciprocal of your probability of success. So the smaller the probability of success, the larger the mean will be. So what it's saying is, remember our mean is like as an average. So on average, we would expect to perform the experiment more times if our probability of success is small. If the probability of success is big, or big meaning close to 1, like 0.9 or 0.95, then the reciprocal of something like 0.95 is just a little over 1. So, you'd expect to do the experiment like once or twice in order to see that success. So at least in this way, this particular formula, at least intuitively, it kind of makes sense. And then here, this whole idea of, okay, you want to see R successes, right? So you want to have a sequence of those R successes, and again, dividing by the probability of success on any given one of them will give you, on average, how many experiments you could expect to perform. All right, so at least again, I'm trying to give you a little intuition behind these particular formulas. They're not having to deal with the counting coefficients and so forth. Isn't the easiest thing, and the reason in particular is because now your sample space is countably infinite. So you end up dealing with a lot of like infinite summations and infinite series, right? Okay, so that's kind of that's the description of these two. Let's see if we can go ahead and do just a simple example to illustrate what this is all about, right? And I'll describe a little scenario. And what we have is, okay, so we have an oil company, right? So we have an oil company. And what this oil company does, it does exploratory drilling, right? That does exploratory drilling. They want to find oil, right? And there is a 20% chance, that's a big chance, right? A 20% chance of striking oil on any particular trial, if you will, right? Let me fix this. This looks messy, right? So they have a 20% chance of striking oil on any given drill, right? And then our question is, so we'll ask a couple questions. So part A, what is the probability that what is the probability that the first strike comes on the third well drilled, right? So that the first strike of oil comes on the third well drilled, right? So this one is going to be your geometric, right? Because you're looking for that first success, right? But I'll just show you that even if you don't realize that it's the geometric, again, it would still apply if you went to the negative binomial formula and just kind of said, okay, r is equal to 1, and you didn't really click that, hey, I could have used the geometric formula, right? So let's set it up. All right, so like I said, R is 1 because that's that first success, right? And then our P in this case will be the 0.2, 20%, right? And yeah, and then we're asking what is the probability that X is equal to 3, right? So in this case, let me write it down. X is going to be, now again, I'll state it as the negative binomial, right? That's the most general case. So I'll say it's negative binomial with r of 1 and p of 0.2. So let's write down, again, in the fullest sense, what the PDF will look like. So it's x minus 1, right? So that one, so we'll have your x minus 1 choose, and then that's where you'll have your r minus 1, which is 0. So you'll end up having r minus 1 there. And then you're going to end up having your just a p to the rth power, right? So that, again, I'll put everything in and then simplify in the next step. And then you'll have your 1 minus p to the x minus 1 power. And then x can take on values 1, 2, 3, and so on. But again, if you set this up so you have x minus 1 choose 0, and then you end up having your p, so that's 0.2 to the first power, and then that's 1 minus 0.2 to the x minus 1 power. But if you set this up, here's why it ends up always being 1. Because you'd have x minus 1 factorial over x minus 1 factorial and 0 factorial. So then the x minus 1 factorial goes away. You have your 0.2 to the first power, and then your 0.8 to the x minus 1 power. So the PDF simplifies to this 0.2 times 0.8 to the x minus 1, right? And then we'll have this, and so on. All right? So now if we want the probability that x is equal to 3, right? So we have to perform this drilling process 3 times. So the probability that x is equal to 3, well, that's simply f of 3. So plug 3 in here, and we're going to get 0.2 times 0.8 to the 3 minus 1, so that's 0.2 times 0.8 squared. And again, the way you can think about this, in fact, let me write it this way. So 0.8 times 0.8 times 0.2. Again, each of these, think of it as a trial. It's either a success or a failure. And you want to have the first success on the third trial. Well, the probability of that happening is this. you'd have to fail on the first and fail on the second and then succeed on the third. But because the trials are independent, you'd get to multiply these individual probabilities together because these are all and probabilities. So that's where independence really does simplify the model, and this ends up being 0.128. All right? So that's what it looks like if we want to figure out what is the probability that our first strike of oil comes on the third well that's drilled. All right, let's do another one. Let's see, part B, same scenario. What is the probability that the third? So what about getting the third strike of oil, right, on the seventh well drilled, right? So now this is definitely not a geometric because we're now looking for the third success, and we want to know what is the probability that it's going to take us 7 trials to get that third success, right? Now, each time you look at a different number of successes, that's a completely different negative binomial random variable. So now it is going to be negative binomial, so NB, and the parameters now are R is 3 and our P is still the 0.2, right? So the PDF in this case, it's going to be, so again, it's x minus 1, choose, and now it's going to be r minus 1, so that is 2, and then we're going to have p to the rth power, which is 3, and then 1 minus p to the x minus r, so x minus r, right? And in this case now, our x would have to go from 3 to 4 or 5 and so on, right? So let me just go ahead and plug the 0.2 in. So it's x minus 1, choose 2, times p to the third, p which is 0.2. So times, and then 0.2 to the third power times 0.8 to the x minus 3 power. Let me put those in parentheses. Right, so we don't get the decimals and the multiplication things mixed up. All right, so that's our PDF for this case. And then if we plug our values in, so we want to know what is the probability that x is equal to 7. So that is f of 7. So that's going to be now 6 choose 2, and then times 0.2 to the third power, and then 0.8 to the, what's that, 7 minus 3, so that's to the fourth power. Now, when you're setting up your negative binomial probabilities using this PDF, when you get to this stage, make sure that these two powers add up to your number of trials, because this is saying you want to have 3 successes and then 4 failures in the first 7, or in these 7 trials, right? So you have 7 trials total, which will be comprised of 3 successes and 4 failures. So you want to make sure that these two powers add up to the value of your x, right? Okay, so let's write down our C choose 2, 6 choose 2. So we got 6 factorial over 4 factorial times 2 factorial. And then we have the 0.2 cubed times 0.8 to the 4th power. And that comes out to be 0.049 if we round to 3 decimal places. All right? Okay, so that's B. So that's, again, just showing you how you can approach all of these as long as you recognize now that it's the number of trials that is the random variable, and you have a fixed number of successes. If you always start with the negative binomial, even if it's you looking for the first success, it will still work. It's just a little faster if you recognize that it's geometric. Let's do one last part of this question, if you will. Let's find the mean and variance of the number of wells that should be drilled if the company wants to set up 3 wells, right? So let's find the mean and variance. So the mean and variance of the number of wells that must be drilled, right, to have 3 producing wells. To have 3 oil producing wells. To have those 3 successes, right? So it's this one, right? So that distribution is the same. So let me just restate it. So it's negative binomial, 3 successes, a probability of success of 0.2, and then the mean, right? So on average, how many wells are they going to have to try to drill? Well, it's for the negative binomial, it's r divided by p. So it's the 3 successes that we want divided by this, relatively small number, and this ends up being 15 wells, right? And then what's the variance? Well, the variance is your r times 1 minus p over p squared. So it's your 3 times your 0.8 over your 0.2 squared, and then that gives us 60, right? And then if we wanted to find the standard, and we could go ahead and write down the standard deviation. It's just the square root of 60. So the standard deviation of the number of wells that need to be drilled is the square root of 60, right? So this, in terms of units, this would be wells squared, and then this would be back in terms of wells, just because of the process of finding the variance, where you have to do that square deviation. Well, we don't need that process now because we have these specific formulas, but it still is reflected in the units being squared, right? Whereas this one would just be units. All right, so that's the negative binomial and the special case of the geometric random variable. But keep in mind how it relates in some regard to the binomial, but then how it differs. It's really the fact that the number of trials now is not fixed. What is fixed is the number of successes we want to observe. Right? See you in the next video.